It's a great pleasure to present the first speaker of this morning, Sebastian van Strien from Imperial College London, and he will speak on the Palis conjecture and stochastic stability.
Well, thank you very much for giving me the opportunity to talk here. It's more than 30 years ago since I came here first. The first time I came to Imperial was actually in the old building, and actually it was just at the cusp. I think halfway during my stay, we moved to this building. And so it's more than 30 years since I've been here at Imperial, and it's always a great pleasure. And in particular because, yeah, it's great to be part of this great project, this Palis conjecture and things that are related to this. So I want to talk about stochastic stability, but I'll first give a sort of a broader background to this. And the first thing I want to mention is I'm going to set myself during this talk entirely in the one-dimensional setting. And in this setting, there, well, let's assume the maps that we consider are just real analytic, although you don't need to assume that, but let's stay away from technical points. And then there's always a set of full measure. And for the set of full measure, you'd like to say what the attractors are. And for every point in this set, there are three possibilities. Either you have a periodic set, a periodic point, which is attracting, or this point in this set X go to a counter set. Or the third possibility is that you have a number of intervals, and this point in this set X goes to these intervals. So in that sense, it's very simple. You have three possibilities: periodic, counter set, or intervals. And nothing seems to be easier than that. And in fact, you can even say the following, that if you take a set of polynomials, then each polynomial can be approximated by a polynomial which is in this class. So this situation occurs densely. If you pick, there exists a set of which is dense of maps, so that all the points from this set X are attracted to this periodic orbit. So almost every point is attracted to a periodic orbit. So this is hyperbolicity is dense. And this was proved first in the quadratic case by Lyubich, and independently by Gracik and Schwantek, and then 10 years later by Kozlowski, Shell, and myself in the general case. And a corollary of this is that structure stable maps are dense. So this seems to be like the end of the story, but actually that's not really quite right, because if you take polynomials, you can also say, well, we're not allowed to sort of perturb things, but we actually ask, let's take a typical polynomial, and in the sense of taking coefficients randomly, so in the point of sense of measure. And then already in the 80s, there was a result by Jacobson, which says that there exists a set of parameters of positive Lebesgue measure, so that if you pick this A from this positive set, then each of these maps has an absolutely continuous invariant measure. And that's quite the opposite of having a attracting set. It's not hyperbolic. And in fact, you can prove even more, and that's, of course, this result of Bennis-Carlsen, that there's a set of parameters of positive Lebesgue measure, so that if you take one of these maps, say in the quadratic family, then in fact you have this growth, which is again the opposite of having a periodic attractor, because periodic attractor means that orbits are, critical points are attracted to these attracting sets, the attracting orbits, and so again that's the opposite. And maybe I should emphasize that there's a sort of similar results in the multimodal case, Tsuji, that's going back a bit, and then more recently by Gao and Shen. And I'd like to make some advertisement for this, because I think this is probably one of the best results in this area.
Is this just within polynomials?
No. And let me just make a remark, because I come back on this again and again, about the method of proof. Now, if you take, in this setting, then you need to construct a set of parameters of positive Lebesgue measure. Not a full Lebesgue measure, but of positive Lebesgue measure. So the method of proof is the following. You throw away parameters you don't like. And so in the terminology of one of the previous talks, you have sort of a little exam, and you check that this exam is satisfied. If it is satisfied, you keep that parameter, and that exam is sort of done on each level. And what you hope to obtain is that there's a set of parameters that remain passing the exams. And the main point is that, or one of the main points is that you still keep some kind of control over how the spatial and the parameter depend on each other. And this is sort of one of the main features. The space parameter dependence has to be still under control. And this is quite easy if you have a lot of expansion, because then you can sort of control this space parameter dependence quite well. But if you don't, then of course that's a different story. But anyway, this is the Bennett-Carlson thing. And of course, there's sort of two-dimensional or high-dimensional versions of this. But I think this is one of the stronger settings here. Because here, actually, just to sort of a little technical point, this actually doesn't require that the maps you start with have to be very good. They actually can have very, very weak growth. And I may come back on that later. So anyway, the upshot is that there exists a dense set of maps which are good, that are hyperbolic, and there exists a positive Lebesgue measure which are not so good and which are not structurally stable, but actually, you know, they may still have other good properties. And so, is structural stability the right concept? And so I think this is one reason why Palis proposed this conjecture and saying, well, is there a set P in the space of real polynomials, or maybe in some bigger set, and with the property that this set is dense and also has full Lebesgue measure, and that each of these maps is stochastically stable. And I'll need to explain what that is, and I'll do that actually only towards the end of my talk. But the idea is to replace the notion of structure stability by some other notion of stability, stochastic stability. And so stochastic stability, sort of without being technical at this particular moment, means something that you have a certain continuity property of invariant measures. And so first, the original map that you need to consider or want to consider has to have some kind of good measure. And a good measure would be a physical measure, and I would like to define this in the following way, that if you take a measure, you call it physical, that if the basin of this measure, namely this set of points, so that for any continuous function that you care to choose, the Birkhoff conclusion of the Birkhoff theorem holds. If that's true, then that's the set of B M, the basin, then that has to have positive Lebesgue measure. So the set of points for which this holds for any continuous functions has to be have positive Lebesgue measure. And so the Palis conjecture would be that within a generic parameterized family, the set of parameters for which you have this well, such a physical measure, and preferably only, finally, many of those, that this has full Lebesgue measure. So that's part of the statement. That would be sort of the counterpart of stochastic stability, but the first part would be that within such a family, typically you have a physical measure and only finally many. So that would be the first part of this. And so for the first 15 minutes or so, I will talk about that. And then I will sort of move on to the stochastic stability. All right, so in fact, just to sort of show the other side of the coin, what are the bad maps? What are our enemies? And there are some bad maps, and they are bad for various reasons. Well, particularly the maps that are Hofbauer and Keller constructed have various bad types of behavior. For example, one type of bad behavior could be that you do have a physical measure, but it's something crazy. So for specific maps that you can construct, it's possible that almost every point lingers most of the time near a repelling fixed point. So these orbits come close to the repelling fixed points, go away, come even closer and go away, and so on. And so these repelling fixed points, which, morally speaking, should be not attractors, are in that sense attracting. So it's still good in the sense that you have still a physical measure, but it's a weird physical measure. And for some other bad maps, you simply do not have any convergence. So if you look at these averages, so these averages of these things, there's just nothing that converges. And this implies in particular there's no physical measure. So you have maps, plenty of maps, that have no physical measure. And another type of bad behavior is sort of more wild in another sense, namely that you may have maps within actually very simple maps, sort of polynomial maps, so that if you look at that there's a counter set which is attracting a set of positive Lebesgue measure, in fact a full Lebesgue measure, but this counter set is not attracting from a topological point of view. The basin of this attractor, the set of points that are going to this counter set, is actually not of, is of small Berg category. And in fact, typical points from the topological points go to an attractor. So you have this dichotomy here that this counter set is attracting a full set of Lebesgue measure, full sets, Lebesgue full sets, and these intervals are attracting Berg category sets. So the big Berg category. So that's kind of wild because you clearly see a dichotomy between what is an attractor in the topological and the metric sense. So these are also maps that you do not really want to sort of call nice. And just sort of as a keyword, the proof of this thing is related to random walks, and that's the kind of point of view I want to sort of advertise a bit during my talk. And so the upshot is there are many bad maps because they have no physical measures. There are also wild maps where the topology and the metric behavior are different. And, well, just as a sort of a counterpart, wild attractors cannot actually happen in real quadratic maps. This was shown by Lyubich and by different methods by Shen. However, for polynomials of higher degree with non-degenerate critical points, they surely can exist. And so let's now discuss, what are the behavior, what is needed to get a good map. And so I will discuss that first. And one of the nicest ways to have a physical measure is one which is absolutely continuous. So that's what I want to first discuss. And there are various conditions, and I will sort of assume here that, that these maps have negative Schwarzian, although I think that's not really necessary. You can replace it by other conditions, but I want to state it as simple as possible. So, of course, there are various conditions that are kind of sufficient. For example, Miserevic's condition is one of them, which says that the critical points do not enter a neighborhood of the critical points. So forward iterates never come back close or never accumulate to other critical points. So that's the Miserevich condition. And then later there was a condition which I will sort of call it Ekman, although maybe strictly should be called Ekman-Nowitzki, because Collett-Ekman had two conditions, like this one, and also a backward condition. And it was Nowitzki who showed that the second condition applies this one. And so you have this condition as a sufficient condition for having invariant measures. And then actually, together with Thomas Nowitzki, in the 90s, we proved that condition, some sort of summability condition, also was sufficient. But actually, more recently, we proved that it's not, no growth condition is needed whatsoever. It's enough to show that the derivatives are eventually big enough. So that exists a constant which depends on the qualitative properties of f, the C2 norm and things like this. And so if these derivatives are bigger than this constant C for every critical point, then exists this invariant measure. And just to sort of, you may not want to see this in terms of derivatives, you may want to see this in terms of scaling. And there's actually a condition that says that, well, if you take an interval in, and you take the first return map to this interval, And so this first return map to this interval may have many different branches, and then the so-called central branch, which we call in plus 1. And it's sufficient to show that the ratio between these are not too big. So that exists an epsilon, which is kind of universal, like this universal thing. So if this holds, then again you have an invariant measure. And just to counterpart that with a result of Martens and Nowitzki, which had something similar, but there they need to show that this ratio goes to 0 in a summable way. So this is sort of the state of play there. And actually, there's also a multimodal version of this, which shows backward contracting is enough. And this backward contracting I won't explain here. But actually, just to sort of make one more comment is that what is quite remarkable is that Rivera, Letelier, and Shen showed that you even have some kind of decay of mixing in this context. And that's rather surprising to me because you have no growth whatsoever. You only have that these derivatives here are sort of big. There's no kind of asymptotic growth behavior. And nevertheless, you have this polynomial decay of mixing. There's some sort of intrinsic. Well, it's faster than any polynomial. All right. And just to sort of make a comment, of course, what are the methods of proof? And of course, proving something exists, well, there's sort of various methods. One is sort of using a function analytic tool setting. So then you have some Banach space, and then you have some contraction. And this is what was used a lot in the hyperbolic context. And then, of course, a very popular approach is also the Young towers, and that's the second approach. And I would like to sort of advocate a slightly more flexible approach, which is not so far away from the Young towers, but it is kind of much more like a random walk scheme. And so basically, all you're trying to do, that's the only thing you need to do if you want to construct the existence of invariant measure, is something of this type, that you want to show that the inverses of small sets remain small in some controlled fashion. And I've written here the precise control we get. That's all you need to do in order to construct an invariant measure. Once you have this, existence of an invariant measure is sort of an easy step. And what's the idea? Well, you take some interval and you take this pre-image set, which consists of many components. And what you're going to do is you're going to see, well, you have this component. Let's draw something. And you have here some sets. And you have some component. Now, maybe some components are sort of good because actually they're sitting in branches that are big. And so here you can sort of estimate the size of this pre-image simply by saying, well, this is small compared to this bigger branch. So this is good because you have this big extension that is going over it. So the other parts might be bad because here the components consist of many sort of non-diffeomorphic branches. And there what you do is you sort of use some kind of induction. You kind of develop this pre-image and you sort of unravel it. You use some kind of inductive method. And in some sense, you look at all these different pre-images and you sort of, you have these different pre-images and you sort of bundle them together in some appropriate way, and in that way you can get an estimate. And the point I'm trying to make is this is sort of much more like a random walk approach where you say, well, you look at the full history of something. And in fact, that's also the way one of the proofs was written, as sort of a random walk approach, where in fact you can actually see the description as you have here a sequence of intervals, and each of these intervals could be considered as a state, and then you sort of develop something where some of the points move left and some points right, and you sort of unravel it in that way. And so that's perhaps the difference between Bernoulli, where you go to fixed scale, and Markov, where you have sort of a situation that elements go to other elements. And here it is a countable Markov chain then. Anyway, so we have good conditions for the existence of these invariant measures. And now the question is, do these maps that have these properties appear frequently? And the answer in the unit-critical case is yes. If you take maps of, say, this type, then, in fact, for almost all parameters C in this family, then you have a dichotomy. Either you have an absolute continuous invariant measure. And in fact, there's some call it Ekman condition that is associated to this. Or the alternative is you have this hyperbolic behavior. So in other words, you have either this setting, which is the hyperbolic one, which of course corresponds to open sets of parameters, or you have this setting, but with the added information that there's some good physical measure. In fact, it's absolutely continuous, and it's a very kind of good setting. And of course, this theorem was proved in different generalities, first by Lyubich, and then sort of in different extensions with various people. And yeah, this statement can be made much broader, and I won't sort of, and I've actually sort of left some names out, but not on purpose, but. And what's the idea? Well, the idea is, in some sense, let's think about the Bennis-Carlson setting. Bennis-Carlson is also trying to sort of show some kind of growth behavior. But there, the situation is you can throw away open sets of parameters. Here you cannot. Here we need to show that for a full set of Lebesgue measures, something happens. So if you take a parameter, you're never allowed to throw it away. You're only allowed to sort of, in the limit, sort of remove things. So even parameters which correspond to very poor expansion need to be considered. And one of the aspects that's kind of really challenging there is that at that point you know very little about the phase parameter relation. Because if you have some good growth condition, then you can estimate how fast the critical points or something move as the parameter moves. That's not so possible, or at least not so easy, if you have sort of a general situation. But actually here the complex methods are coming into play. And this is why actually if you have a unique critical point, a map with one critical point, you can still recuperate this or recover this information. But there you use sort of a lambda lemma. And unfortunately, because of this, you need to restrict your situation to the case where you have one critical point only. And well, we're making some progress towards this, but using different methods. But as a kind of delaying tactic, I'll sort of move a little bit away from this. Anyway, let's just make an upshot of what we discussed so far. In a unit critical case, we know that most maps have physical measures, but in the multi-critical case, we don't yet know this. In the meantime, let's go back to this Palis conjecture and this question about is almost every map stochastically stable? And so let me explain what I mean by this. So I'm going to set myself in this situation where you have a class of maps. Not one map, you don't iterate one map, but you sort of have a set of maps. That's the set omega epsilon. And they may be of this type. So F is a specific map. And then you have some sort of whole neighborhood or some set of maps which contain this given map. And this epsilon refers to that these maps are all epsilon close to the original map F. And then you put some measure on this space of maps. So in this case, of course, you could take just the Lebesgue measure on this interval minus epsilon epsilon. And then what you do is you're going to, given a map, F, well, maybe I should have written G here. So that means that at every step, you choose an element from this. So in other words, you choose a different map at every stage. And then you iterate a point by a different map every time. So instead of mapping one map, you might iterate a number of maps. So, for example, it could be that you have three maps. Your original map, one which is slightly bigger and one which is slightly smaller parameter. And then you sort of choose at every time a coin and say, well, I'm choosing my original map or my bigger map or my smaller map, and then see what's going to happen. And then you call for this what is called a random system, measure invariant if the following holds. So this is a measure that you'd like to sort of say is invariant. And the definition is almost the same as the usual one. When do you call an invariant measure, a measure invariant in the usual context? Well, if you have one system, you just call it invariant if this always holds. So that's the usual definition for invariance. And instead of doing that, you're saying, well, let's sort of integrate that. So we don't have one map, but we have a set of maps, and so we're going to integrate this. We're going to look at the inverse, but for all the possible g's that you have in this set, and so we take this measure in this thing here. So in this case, the back measure on minus epsilon epsilon, and consider whether this average is the same as the measure you have originally. And here I should have written mu epsilon a. So for every a, this should hold. All right, so, and then a measure could be called physical if the following holds, that if you take for almost every point x, g in this product, so here you have the interval, the back measure on this interval, or your phase space, and here you have this sequence of maps. So at the first iterate, G0, G1, G2, and so on, like here. And here, of course, you can define this product measure on this thing here. So for almost all points in this product space, you want that if you take the iterates in this fashion, that the average goes to this Lebesgue this measure that you want to call physical. So that's what you call a physical measure, if this happens in the weak topology. So that's an analog of the previous situation of physical measure. And so let's take a map and assume it has a physical measure, and then define when we can say that this system is stochastically stable with respect to some random system. Of course, you have to talk about what random system you're taking, because yeah, it may depend on what perturbations you allow, whether or not this is stochastically stable. So stochastically stable is with respect to some set of perturbations, some random perturbations. Anyway, what you want is that this measure mu epsilon associated to this random system converges into the physical measure of your original map. And you say it's weak stable if it converges in the weak topology, and strong convergence if it's in the L1 norm for the densities. No, and this point of view was sort of taken by a lot of people, and I just mentioned here some names. And the remarkable thing for me was actually to notice that there are actually very few examples to show that things are not stochastically stable. I could actually find very, very few only. It's quite conceivable that any more or less reasonable map is stochastically stable. I mean, the only things I could find, but I'm far from an expert. I really moved into this area very recently. Is this paper by Blank and Keller, where there's some counterexamples, but they're very contrived. So perhaps everything is stochastically stable. That is kind of reasonable. And again, in the methods of proof, there are several approaches. One is the function analytic approach, which works extremely well in a sort of hyperbolic context. And some people use Young towers. And then again, there's a third method, which is slightly more flexible. And I think it's fair probably to say that in the one-dimensional case, surely the strongest result is by Shen, who showed that, well, suppose you have some summability condition. Well, this is not quite the assumption that Thomas Nowitzki and I had, because there we had some 1 degree, but suppose you have here some summability condition. And moreover, this F is ergodic with respect to Lebesgue. So this means you have some kind of mixing, so you have kind of uniqueness that comes from there. And also some conditions on the perturbations. So in other words, you need to make something about, well, do you sort of do additive noise, or do you some sort of other noise? And there are some conditions on that is kind of additive noise, and you want to have that there's some kind of continuity properties on that. And then what Shen shows is that, first of all, that the random dynamical system has a unique physical measure. And moreover, that this map is strongly stochastically stable. And I think this is, as far as I can see, this is the strongest result in this case. So here we're talking about the general multimodal maps, there's some kind of regularity conditions that are needed, but this is really in a general multimodal context. And you can ask questions like, take this bad map of Hofbauer-Keller. For example, the bad map where the repelling fixed point is this physical measure. Is that stochastically stable? And of course, if you think about it, what these stochastic, these maps are made of is things where you almost have a sort of invariant box. I mean, in these constructions of that are essentially that you have a map, some map, and then on a very small scale and on a very high iterate, it's almost renormalizable. And so it takes a long time for these points to sort of escape, and then these invariant boxes are created, so a lot of them are near this repelling fixed point. The orbit of this, this box is made so there's this repelling fixed point. You know, here's the original map, and here I take some iterate of the map, and here I have this repelling fixed point. So what you do is you sort of make sure that a lot of these forward iterates of this almost periodic interval are sitting here, which means that a lot of the mass, most of the time, the orbit spent near this repelling fixed point. Now take a stochastic perturbation. Of course, this means you add some noise. So very quickly, these points are iterated by things where you sort of move out. And of course, there's a fight between that, because on the one hand, they move out, and they're kind of free to do what they want. And so the invariant measure might be sort of much more sort of smoothly distributed than is the case here. At the same time, of course, they get trapped back in here. And my sense is that actually it will be stochastically stable in this case, but there's something to prove. It's not a trivial matter at all. And of course, there's various other cases, where we test cases to consider. So one of the test cases that I sort of had a look at, with Vaishou Shen, was the following. And, that was partly because people were kind of not answering this question in full. So suppose you have a map, which is like this. So here is the map that we consider. And the feature of this map is that there's two parabolic points. And it's a map of the circle, covering map of the circle. And, actually what is well known, and actually well known for years, is that if you take this alpha, so let me just write it here in the figure. So you take here, so here there is sort of a contact, and if alpha is between 0 and 1, then in fact there's an absolute continuous invariant measure. And on the other hand, if alpha is bigger than 1 or bigger, then most points will stay most of their life near this repelling fixed points. So there's this dichotomy. And so what was known is that if you take some random dynamical system, and this was done by these two authors, that if you take alpha between 1 and infinity, then it's stochastically stable. So in other words, if you take alpha bigger than 1, and you take some perturbation of the map with sort of additive noise, then in fact the measure which is absolutely continuous, there's an absolute continuous invariant measure for the random dynamical system, so this has some sort of density. But what will happen is that the density sort of degenerates, and in the limit measure, corresponding limit measure, converges to the direct measure. And in the case where alpha is between 0 and 1, actually nothing was known, in the sense that it was known that if you take the limit of the measure of this random dynamical system as epsilon goes to 0, then it was simply merely known that the limiting measure was a linear combination of the Dirac measure sitting on this fixed point and the absolute continuous invariant measure, which is sort of associated to the case here when alpha is less than 1. So that was the setting here. And what Alves, Freitas, and Valiente, and also some other people, I think, asked is the BOF map actually strongly stochastically stable when alpha is between 0 and 1? And so this is, the new result in this talk, is that if you take a random dynamical system which is of this type, ft is f plus t, with t uniformly in this interval, then first of all this has an invariant a physical measure, an absolute continuous invariant physical measure for this random dynamical system. And secondly, this map is strongly stochastically stable in the sense that if you let epsilon go to 0, the density of this measure converges in the L1 sense to the density of the measure for the original map. And so the dynamical system that we consider here is you take a map, you iterate with ft0, where ft0 is sort of just, you add some constant, here you add some other constant, and you take this composition, and you sort of let this ti be uniformly in this interval. And that's the kind of the setting that we have there. And just to kind of give you kind of a hint of the methods, is that, and I think the main point here is again distortion. Because if you take here sort of a time of the following sense, you take a point and you take a sequence of perturbations, sequence of TIs. And now what we're going to say is we call this time m, the minimal integer, so there exists an interval containing this point x, so that this composition of different maps onto an interval of fixed size tau. And now the main point is that the distortion has to be also bounded. It's very easy to get to this fixed size, because after all, if you go through this fundamental domain here, even though we cannot actually iterate this particular map, then it's quite easy to sort of get to something which is roughly of this size, even though you iterate different maps every time, but still you can get to big size. The real point is to get to this bounded distortion. And so that's this set here. And the difficulty, of course, is the parabolic points, because that really will precisely fight or cause troubles with this bounded distortion. And for that reason, what you actually need to do is to go through this parabolic case many times. So what you have this point x, it will come through here, and you may have to sort of go out, come back, come out, and many times before you get actually a good time. This good time is when you have this bounded distortion also. Not only you go to this fixed size, but also to some fixed distortion. And then the main point is to show that you have some kind of rate of control for the set of parameters for which you have to wait a certain amount of time to get this, this good situation. And that has to be summable, and that's, of course, what this is saying here. And then the point is that you want to construct what we call randomized sets. Well, what's a nice set? Well, the nice set is sort of, in the sense of Martens, is a set so that if you take the boundary of an interval, that you do not come back inside, which allows you some kind of Markov construction. And here, of course, we have random sets, and of course, random sets means that you have for each sequence of TIs a different set. So this random set is something which is kind of a collection of sets depending on each sequence of TIs. Choose. And then you get into a Young Tower setting, and then you sort of get into standard techniques and so on. So I think I'll stop here, because otherwise I'll go too technical. Thanks very much.